Good morning, everybody. Welcome back again to my lecture series. This is my third and last lecture, so that's perhaps the news. Okay. Previously, in the last two lectures, I've been talking about what's the structure of ice in contact with a vapor phase. And we've seen that the surface of ice in contact with its own vapor exhibits what we call surface premelting. Okay? In this third lecture, I'll talk about a related topic, which is what is the structure of ice in contact with another substrate. Okay, so instead of vapor, now I have a solid on top of ice. And we'll see that there is also some room for premelting, but we call this interfacial premelting, to distinguish from the premelting we get in contact with vapor. And I won't talk about it in an abstract sense, but for one particularly very interesting application, which is ice friction. Okay, so I'm going to talk about ice friction and what insight can we get from my tools, which are mainly computer simulation, molecular dynamics by computer simulation. Okay, so it's an interesting topic which has a very nice history, which it's amusing to talk about a little bit, because ice friction is a very useful property that has been used by humankind for many, many years. There are documents of exploiting the slipperiness of ice for transportation of huge weights. So the fact that ice is slippery has been used for mainly as a means of transportation. It can be goods, or it can be people, or sometimes just for the hell of leisure. Okay, and it's also a matter of concern because it can provoke hazards in cold regions. The fact that it's very slippery, so you can exploit it as a useful thing, but it can also have some drawbacks and make things dangerous when you try to brake with your car on slippery ice. Okay, so it's an important topic. And it's one topic that it's not exotic in the sense that I think that everybody has had some encounter with slippery ice. So it's a very familiar property, and perhaps because it's very familiar to anybody without even stepping into the lab, it's actually a very controversial topic. Okay, and it has been a matter of controversy ever since it was a matter of inquiry, of scientific inquiry. Okay, so my story starts with Faraday, which made one hypothesis, which is far less well known than other more important hypotheses he made, is that ice below its melting point is covered by a thin water layer. Okay, so the first suggestion that there exists pre-melting was done by Faraday. Yeah? He made some experiments with cube ice and concluded that the explanation for his experiments was that there should be some pre-melting. Okay, but this was in 1856. Okay, thermodynamics was being formulated at the time, and it was not that well understood. And definitely, surface thermodynamics had not been developed yet. So what Faraday was actually saying for the people at the time is that you were violating the phase rule. He was saying that you could have three different phases below the triple point: ice, water, and vapor. So his fellows didn't they were not convinced. What is your opinion on this now? What?
A pretty smart guy.
Yeah. So you better trust him. Then that is a matter of faith. But you would be on the right side. No, what we know is that this is not a bulk liquid phase. So it's not violating the phase rule. It's not a bulk liquid phase. It's a microscopic thin film, a surface layer that is stabilized by an external field. The external field is the field that emanates from the bulk ice. Okay, so we understand this is no problem today. Okay. But at that time, a fellow of Faraday, James Thomson, he was really smart, and it seems to me before perhaps the Clausius Clapeyron equation that Rob has been talking about. He made some thoughts on entropy and concluded, I just don't know how you conclude this without formal thermodynamics, that because of the density difference between ice and water, ice should be melted by pressure. So he was the first to suggest that if you compress ice, you melt it. Okay? And so, according to Faraday, if you have a spontaneous layer of water on top of ice, then his followers argued if there's spontaneous layer already there, then you put a slider on top of ice and you have a lubricating layer. So that's a nice explanation for the slipperiness of ice. James Thomson had another idea. He said, I do not trust that you can have a surface of melted water on ice below the melting point. So it's bare ice, but once you put your slider on top of ice and you step on the slider, you create pressure, you drive ice to its melting pressure, and then you get the lubricating layer. Okay, so that was James Thomson's argument. And they argued strongly, to the point that John Thomson had to go and talk with his big brother. And he said, look what Faraday is saying. He's not willing to abide to my statement. And, well, his big brother was Lord Kelvin. Okay, and he did the first experiments to prove that, indeed, you can melt ice upon compression. Okay, and Thomson was supported by Reynolds and then by Helmholtz. So this theory prevailed completely for many years. Until about in the 1930s, Bowden and Tabor, who are perhaps less well known, but they are thought of as the, say, the beginners of the science of friction, known as tribology. They argued that they made some back of the envelope calculations and said, look, the pressure you need to melt ice at -10 is so huge that we can hardly trust that you ever get to the melting pressure. So it cannot be a lubrication layer due to pressure melting, okay? And they argued it's the motion, the initial motion of the slider on top of ice, which will create heat and then drive ice to its melting point, and then you'll get a lubrication layer, okay? So those were the initial controversies. And this last theory, I think it has been the prevailing theory ever since. One reason that it's a prevailing theory, I think sometimes we have these biases, is that it can be nicely theoretized. And it can be nicely theoretized in the context of an interface school of multi-phase flow, okay? In this theory, you start from the definition of the friction coefficient, which is the parallel force you exert divided by the perpendicular force created by the weight on the slider. That's the definition of the friction coefficient. And you say, okay, if we have a meltwater lubricating film, whatever its origin is, if you assume you have a meltwater lubrication film, then you assume that the lateral force will be given by this plain Newtonian law. It's viscosity times shear rate. And you assume that the shear rate will be just the ratio between the speed of sliding divided by the thickness of the lubrication layer. Okay? So that's a plain and simple rule. And then you just need to plug this here and put it there to get a theory of friction. Now, the problem is you don't know what the value of H is. That's the thickness of the lubricating meltwater layer. And here it is where you make a nice energy balance. Okay? You say the evolution of the thickness of this film, the evolution of this filmness, will be due to two reasons. First, because you slide, you create heat, and this heat will melt water. Okay, so you get heat of a rate. This is the rate at which you create heat. That's the power. It's going to be the force, the lateral force, times the speed at which you are moving. So that gives you a rate of heat dissipation into the ice, sorry. And then you divide this by the latent heat per molar mass, and what you have is the amount of mass that is being melted as you slide. So that's a favorable process that will increase the thickness of the meltwater layer. But then because of the flow, there are couette flow and squeeze flow that move the meltwater out between ice and the slider, and that depletes the meltwater layer. And then eventually you invoke a stationarity condition, say, okay, let's assume we get a stationary state, then this will become 0. And what comes out from this balance is an explicit equation for the lubrication layer thickness as a function of water's viscosity, the speed of sliding, the latent heat, and geometrical details. And then you plug that back into this equation, and you get a nice equation for the friction coefficient. It's explicit, it's not just the scaling law. So it's a nice theory of the friction coefficient that gives widely different regimes, okay? For small velocities, it says that friction increases with speed of sliding, while it decreases with speed of sliding, while it increases with speed of sliding when it's thick enough. Okay, and these are the prevalent theories, I believe. But being positive, you could argue, okay, there's some controversy. I'm not sure who's right, but at least there is some consensus in that the origin of ice pre-melting is the presence of a lubricating water layer. It could be spontaneous pre-melting, pressure melting, dissipation of heat, who knows. But this was a long time controversy, and now if you're a curious student, you say, okay, there must be some modern opinion on this, so I'm going to enroll into the interface school to get it sorted out. Okay? So imagine you had this thought 3 years ago, and you attended the first conference, the first interface school, and you find this light to start with. Okay? Takes a few seconds to digest. Okay, so there's a controversy on the nature of the water lubrication layer, but there's also a controversy on the role of this lubrication layer. And some folks will argue there's no significant role of this lubrication layer at all. Okay, and this is an argument put by Daniel Bohn and his group, and by other very smart scientists like Derjawin. In the 60s, Derjawin also suggested that ice friction had nothing to do with lubrication. And Derjawin is the guy who invented the concept of disjoining pressure. Okay, so it's a big issue. We're not altogether sure of what is going on. So let's try to understand what are the arguments put by Bohn, because they're actually quite influential, and I think they have triggered a little bit of additional activity into this topic. Okay, so what Bohn does is to use a tribometer, which is essentially a steel sphere, which is attached to some axis, and you just rotate the sphere. And in this way, you can measure what is the horizontal force you need to perform in order to rotate at a given speed. And then you also control the pressure you exert on top of ice. So the experiment is giving you right away the output, which is the lateral force along the track of the circular track, and the normal force, which is the pressure you exert on ice. And that way you can measure readily the ice friction coefficient. Okay? And Bohn found this curve. Okay? It's friction coefficient as a function of temperature. Okay? And it has a non-monotonous behavior. And he could explain this monotonous behavior by two completely different mechanisms. At low temperature, what we see is that the friction coefficient decreases with temperature. And what he found is that actually this temperature dependence correlates perfectly with computer simulations that were performed. So in computer simulations, you take the ice, and what you do is to calculate what is the diffusion coefficient of the outermost water molecules in the surface along the parallel direction. He did that for some computer simulations, and he found that that behavior, which is shown here in grid, correlated perfectly with his experimental results. So what he argued is that friction at low temperature is due to large mobility of the outermost ice molecules on the surface. Right? You could argue that's an argument that it's okay whether you have free melting or not. But he didn't trust pre-melting, so here is just the outermost molecules. Okay. Then what happens at lower temperatures? Look, you have a very steep increase in the friction coefficient. There is a completely different mechanism, what rules friction. What happens in these situations is that temperature is high enough that ice becomes soft. So the steel ball can indent into the ice texture very well. And then the friction is due to the work you need to do to plough ice. It's like ploughing ice. Okay? And that's a property that is dictated by a material property, a mechanical property of the ice. It has nothing to do with other surface properties. It's called the indentation hardness. Okay? So what's going on, according to Bonn, is that because the indentation hardness is becoming very small, you get a lot of indentation, and then you have a lot of trouble ploughing ice. And the more trouble you get, the more you indent ice, which occurs to a greater extent the softer ice is, that is at low temperature. At high temperature. And that's the second mechanism. Okay? And in view of this, he ruled out the role of pre-melting. But there are two problems these assumptions need to meet, I think. And the first one is that, okay, this is a perfect correlation. It's amazing that his experiments correlated so well with the computer simulations for the diffusion coefficient of the outermost molecules. Okay? But if this is a general trend, you need to conclude that the low temperature friction coefficients are independent of the nature of the slider. They just depend on properties of ice itself. Okay? And that's a problem. So one thing you need to meet is, why is the ice friction at low temperature independent of the counterbody? And is it really independent of the counterbody? And then there's another problem, is that you could explain things in terms of indentation hardness, and that's great. But the indentation hardness is a completely empirical property. So it's not quite an explanation. There are no theories of indentation hardness. Indentation hardness depends on the radius of the steel ball. It depends on the rate of indentation. It likely depends on the material that is indenting, and it depends on the temperature of ice. And if you don't have a theory for that, then you just have an empirical theory for ice friction. So it's not altogether satisfactory. Okay? Actually, there have been some previous experiments of friction coefficients in the literature, and I just take a small set of them. And in these experiments of friction coefficient as a function of temperature for several plastic materials, what you get is the friction, well, it's very much dependent on the plastic material. But not only the actual values, but even the trends can change depending on the material. So we still need to understand ice friction further. Okay? So when I became acquainted with these results, this was 2017, was it? I think it was 2017 when I first saw a conference with this kind of results, and I got attracted to the problem. And I got attracted to the problem because I had just started my studies of ice pre-melting, surface pre-melting. And well, in my simulations, my students would come to me and show me these snapshots. And I can see a nice layer of ice pre-melting. So it's difficult not to expect that this feature of the ice surface has no role in friction. So I decided to get involved into it, and eventually I was lucky to get the visit of a Polish student to my lab, and we started the project. Okay? And so here is what we do. We do computer simulations. Let me explain you this. This array is just putting water molecules in a perfect lattice array corresponding to ice. So that's the structure of ice, viewed from some point. It doesn't look hexagonal, it is, but only viewed in other direction. That's a perfect ice lattice, arranged such that the basal plane is exposed to the surface. Then I take atoms and arrange them in a phase cubic centered structure. That's like a metal. So I am studying ice, and this is going to be my slider, which looks like sort of copper, okay, in its structure. I have the atoms here in the perfect low temperature phase, perfect arrangement of least energy. This is my wall, and I am going to compress ice a little bit, just gently. That is, I'm going to tell these atoms to go down and exert some small pressure on ice, atmospheric pressure. Okay? And then I let my simulation work, and after some time I get my system is equilibrated. can see now that the atoms have moved within their Baukeis, but what I see is that spontaneously there has been formed an interfacial pre-melting film. So that's a pre-melting film between ice and a solid wall. It's actually a bit thicker in this situation than when I study surface pre-melting. Okay? Now, next thing I will do is as follows. I'm going to use a color code. Okay? At time t0, after equilibration, I'm going to color in green some central atoms in the wall. In blue, some central atoms in the lubrication layer or pre-melting layer. Is it lubricating? That's what I want to find out. In the pre-melting layer. In orange, I'm coloring the ice molecules in the center. And then I will shear this system. That is, I'm going to translate my wall. So that's a sliding experiment. Okay? And eventually, from the color, I will be able to tell a little bit what is going on. Of course, I will analyze that quantitatively afterwards. But just to explain you the nature of my experiments. Okay? But one nice thing of the simulations is that we are simulating, in computer simulations, what we do in molecular dynamics is to assume water molecules interact with each other in a specific way that is meant to reproduce the properties of water. So I have a potential of interaction which mimics hydrogen bonding and so on. So it's a nice model. But then I also can change at will how these atoms interact with the water molecules. There's an energy parameter which will tell to what extent do the wall atoms interact with the water molecules. And in this way, I can tune the contact angle. I can tune the hydrophilicity or hydrophobicity of my substrate with the water molecules. So I can do, with the same setup, several experiments on different sliders. Depending on the energy I impose of interaction between the wall atoms and the water molecules, I get different contact angles, from very hydrophobic substrates, from moderately hydrophilic substrate.
Sorry, I didn't understand where is the contact angle in your
There's no contact angle in my previous picture, okay? It's an independent simulation. So before I do the simulations of sliding, I have done independent simulations where I had the wall and I put a water droplet on top of it. I made my molecular simulation and eventually calculated the contact angle.
But there's no shearing?
There's no shearing at all. This is just a way of characterizing the surface. In experiments, you do this often. Right? You correlate properties with the contact angle of the wall, and of course, the contact angle of the walls you get in the lab in a different experiment. The same thing here, okay? So let's see, yes?
What was the color code just before, because it went from 0 to...
You can see it here, okay? The color code is blue for the central atoms in the pre-melting layer.
I meant in the slide before with the contact.
The color code in the previous is just a contour map. So red is very dense, yellow is very not dense. So the yellow is the vapor, and the red is the water.
And it's denser as the contact line.
Yeah, that's right. Here it's denser. Here there's an extent of stratification when the energy of the wall increases. You can see it. Here it's only little stratified. Here it's strong stratified. Okay, good. So let's see what's the outcome of these movies, depending on the contact angle, okay? Here I have my ice in contact with a wall for a hydrophobic substrate, contact angle 120. The problem is, let's see if it goes. No, it doesn't. The problem I have, I cannot see where, there it is, okay? Can you see something? You can see first that the wall has moved, but as the wall moved, orange and blue molecules are at the same place. What does this mean? That these are stick boundary conditions in hydrodynamics. So water next to ice has stick boundary conditions, which are the ordinary boundary conditions. But look, the wall has moved, and the water molecules have hardly moved at all. Okay? Let's continue the movie. Okay? The water molecules are unreactive to the motion of the slider. in hydrodynamics that corresponds to very strongly slip boundary conditions. Okay, so for a hydrophobic wall, indeed, the wall is going through the pre-melting layer with great slip, and I think, yeah.
They move a little bit, so probably if you go to 180, they will not move at all. And they will
Well, there is, even without the hydrodynamic flow, there is diffusion, so eventually they will move. So here, it's hardly detectable, the difference between the flow and the diffusion. Okay? Now, if on the other hand, we consider a hydrophilic substrate, then you'll see that things are very different. Okay?
And the pre-melting layer is also thicker. This is also due to the...
It got a little bit thicker. I'll talk about that later. You very observed a lot of things. What I wanted to draw your attention to is stick boundary conditions between the pre-melting layer and the solid here and here. So now the substrate has stick boundary conditions. So the role of the substrate is to impose different boundary conditions, hydrodynamic boundary conditions. You can go from very slip to plainly stick boundary conditions. Okay, so the substrate does have an important influence, I believe. Okay, so in order to try to understand why is there this shift in the hydrodynamic boundary conditions, now I am plotting density profiles. What I am plotting here is the density of water molecules as a function of the distance away from the substrate, as a function of the distance away from the substrate. And these density profiles have two regions. This region in black, which has sort of two peaks, those are the stratified layers of the solid phase. Okay, so you can tell this is the solid phase, this is ice. But this other region is melted ice, it's the pre-melting layer. Okay, in blue I am showing the part of the density profile that corresponds to pre-melted water molecules. Okay, and you can see from these plots that the density profile for a hydrophobic substrate, not unexpectedly, is very different from that you get for a hydrophilic substrate. Okay, the pre-melting film thickness apparently is actually getting thicker, and you had observed that already in the picture. So what we're going, an interesting issue is, okay, they are different, so the density profiles change with the nature of the substrate. To what extent is the structure of the surface pre-melting, that is, of ice in contact with vapor, representative of these density profiles? We can do that easily in computer simulations. Here it is. In green, I am showing the density profile you get for surface pre-melting at the same temperature. And you can see here very clearly that understanding surface pre-melting is a very good proxy to understand interfacial pre-melting if the substrate is hydrophobic. And it's very similar. Okay, so you can correlate properties of your surface pre-melting film with properties of the interfacial pre-melting film, provided your substrate is very hydrophobic. And this is an observation that has been made in computer simulations many times. Okay, so for example, you draw the density profile of water next to oil, and it looks very much the same as the density profile of the water vapor interface. A hydrophobic substrate is like vapor, so vapor is hydrophobic, if you like. Okay. Now, to follow my study, I'm going to divide my absorption, my pre-melting film, my density profile in three pieces. Okay. Here, to the left of this line, I will call this the wall adsorbed layer. It's the density layer of water that is close to the substrate, to the slider. Okay? And I'm going to study the properties of this adsorption layer. What I will do is take molecules that are in that adsorption layer and measure the parallel diffusion coefficient. So how the water molecules diffuse along the parallel direction, that is parallel to the substrate, as long as they are within the pre-melting, the adsorption layer, because eventually they can move away. Okay? And let's see what happens. Okay? So here I'm showing you the diffusion coefficient of bulk water as a function of temperature. And now let's see how is the parallel diffusion coefficient of the molecules in the wall-adsorbed layer for a hydrophobic substrate. Here is what you get. Okay, at high temperature they are similar, but at low temperature what you can see is that at low temperature the mobility of water molecules in the outermost layer is much greater than that for undercooled bulk water. And I think this is sort of representative of what Bonn observed at low temperature, that the mobility of the outermost water molecules was large. But we observe it in pre-melting films, not just on the atoms adsorbed on bare ice. Okay? If I take the hydrophilic substrate, then things change a lot. The diffusion coefficient is much smaller. The diffusion coefficient of the water molecules adsorbed to the substrate is much smaller. And that makes sense. You've made the observation that close to the wall there is a strong stratification. Why do you get this stratification? Because the water molecules, when the wall is very attractive, are stuck into the wall. Okay, so you get small mobility. And I think this sort of explains why we changed from very slick boundary conditions to very stick boundary conditions. Okay? Now, notice that within my pre-melting film, let's think of this one, I have the wall adsorption layer that I have studied. This is the ice adsorption layer, which is always stick. And in between, I have this region, which you could claim it's the quasi-bulk region. It's the quasi-bulk region of the quasi-liquid layer. And the question is, because in pre-melting theory, in the lubrication theory, you are assuming your film lubricates. The question you can make is, does it really lubricate such a thin film? This film is 1 nanometer thick. Can you expect lubrication? Of course, this is an adsorption layer. It has nothing to do with bulk water. This is another adsorption layer. Is this sufficient to sustain lubrication? Let's try to analyze that. But first, let's look at the diffusion coefficient of that region. Here I am showing what is the diffusion coefficient of bulk water at temperature -7 degrees. These are the diffusion coefficients, parallel diffusion coefficients inside that quasi-bulk region of the layer as a function of contact angle. What I see is that the diffusion is smaller in this confined region than it is in bulk water. This is the value of bulk water. These are the diffusion coefficients I get for different substrates within that region. It's smaller, but it's not a dramatic difference. It's 30% smaller or so. So I write this because sometimes you find in the literature claims that the viscosity of water, of confined water, is 100 or 1,000 or 1,000,000 times larger than bulk water. And I don't trust this. Okay, so people have been doing simulations for many years, and in this community perhaps you don't do simulations. If I had to convey to you one single message about simulations, is that you are doing good with your mesoscopic scale physics. That is, all of the constitutive equations that you use in mesoscopic modeling seem to hold up to the scale of 1 nanometer. We can see that in the simulations. Of course, not quantitatively, but on qualitative grounds, they hold well to impressively small scales. So it takes 1 nanometer for an atom to look at beyond and think it's a bulk atom. Okay, this holds always for simple liquids in my experience. Okay, it could be different for polymers where you have very large scales there, but for molecules of some small diameter, it holds very strongly. Okay, so I get smaller diffusion coefficients, then I expect larger viscosities, but not orders of magnitude different from bulk. Okay, now more powerful. Here are my density profiles. We've already seen them. Yes.
Your previous curve, how does it go with the temperature?
I also missed this when I was preparing my talk, and I don't have it. I should collect that data because I'm sure I have it. Okay. Here are the density profiles. I'm going to show you something more interesting. I'm going to show you the flow profile. Okay, that is the speed of the molecules how fast they move as you slide the substrate as a function of the distance away from the substrate. This is shown here in orange. This is my flow profiles. This is the velocity, it's this scale. The velocity relative to the velocity of the plate. Okay? So here, at this point, the velocity of my molecules next to the wall is moving as fast as the plate. And then it decreases up to 0. So at hydrophilic situations, I had stick here and stick here. So I'm going from the plate velocity to 0. If you know hydrodynamics, you are recognizing here that within the scale of 1 nanometer, I am getting something very close to Couette flow. Very close to Couette flow, okay? Which is the hallmark of a lubrication process. Okay? So that's already powerful, I think. But now let's try to analyze this quantitatively. Okay? So if I have Couette flow, in the paradigmatic Couette flow, my velocity profile as a function of distance away from the wall is a straight line. Okay? I just need to apply my boundary conditions. Okay? So here at sigma 2, where the velocity is 0, that is right next to ice, I will assume, and this is my origin. This is 0 in set dimensions. And here my velocity is 0, so I can rule out C1. C1 is 0. That's my boundary condition. It's a situation where boundary conditions are trivial. Second, at this point, where the flow profile ends, it cannot continue beyond the end of the lubricating layer here. This is my slip velocity, whichever it is. So at set equals sigma 1, and I'm going to define the distance dc as the distance from this point to this point. At that distance, my flow velocity is the slip velocity. And when I do that, I'll skip the details, but the profile you get, U of set, is just given by US, the slip velocity, divided by this Couette thickness. The Couette thickness is the thickness between which the Couette flow evolves. And so I can get my shear rate right away. Sorry, I'm missing here a coordinate. My shear rate is just the derivative of the flow profile with respect to set. So my shear rate is the slip velocity divided by the Couette flow distance. Okay? I could tell just from looking at this what the Couette flow distance is, but I don't want to take this arbitrary decision. So I'm going to assume that this law holds, the paradigmatical law of lubrication. I'm going to assume this law holds, that is viscosity times shear rate. And what I'm going to do is to solve for DC. DC is like this. And from my own simulations, I can measure right away the shear rate, the shear strength, sorry, the shear force. What is the word? Shear stress, sorry. The shear stress, I can measure it in my simulations right away. I just need to measure what is the force exerted by water molecules on the wall. That's my shear rate. I can measure from these profiles what is the slip velocity. And now I'm going to assume that the lubricating layer has actually the bulk viscosity. The bulk viscosity of water at that temperature, which I can measure independently. So from that assumption, I get an estimation of what the Couette distance should be. And then I can draw a synthetic Couette flow profile. Okay? So these are my flow profiles that I showed you before. And these are the predictions I get by assuming that the viscosity of the quasi-bulk region of the quasi-liquid layer has a bulk viscosity. And you see that it's not perfect here, but it's close to right, and it's very good already here for a pre-melting thick and interfacially pre-melted film of about 1 nanometer. So bulk thermodynamics and bulk hydrodynamics, it's being extremely robust for these systems. Okay? So it seems these interfacial pre-melted films, even of 1 nanometer, behave as lubricating layers. Now, it's true. From the simulations, it's true. But what about going to the larger scale, Friction is a problem of large scales. I am doing these simulations in a ridiculous scale, you can claim. Okay? And so I need to meet an important challenge. It's a well-known phenomenon in tribology. Your slider is not smooth, and ice is not going to be smooth either. So all of the weight that you put on the slider is typically supported by asperities. And in those asperities, you have huge pressure, because all of the weight is borne by those. And so assume that my simulations are right, and that I have a spontaneous interfacial pre-melting layer there, which could act as a lubricating layer. That's great. But the pressure that these guys feel here is so large that my lubricating layer is going to be squeezed out. This is a well-known effect in tribology. That's why water is not a good lubricant. Water is a fantastic lubricant, in fact. You want low viscosity. So water is very good lubricant in principle. But because of the squeeze out, water flows away, and then you have no lubricant. And it was useless. That's why you put oil, which is more viscous, but it will stay within the bearings longer. That's why it's a better lubricant. So you can argue, never mind if initially there is any interfacial pre-melting layer. Eventually it's going to be squeezed out, and you're going to be left without any pre-melting. What's your opinion on that?
Wouldn't you recreate a new layer at the direct contact?
Draw your phase diagram. Okay? Not only will it want it to be created, it will want to be created because that's the equilibrium situation, but draw your phase diagram. What is this? At low pressure, you are here. You have some pre-melting film thickness corresponding to a state of low pressure. What happens if you increase the pressure? You are closer to the melting line. So you're stabilizing the pre-melting film further. So it's going to recreate, but it's going to recreate that big, thicker pre-melting film. Okay? It's this situation. You increase the pressure, you approach the melting line, so your equilibrium pre-melting film thickness is going to increase. So this is an instance of Le Chatelier principle. You put pressure, water is evacuated to respond to the perturbation, you increase the pre-melting thickness. Okay? And here I am showing plots of pre-melting film thickness as a function of pressure. At fixed temperature, show pre-melting film thickness as a function of pressure for all my sliders, for whatever contact angle, it always increases. Yes, because it's a general effect. It's a thermodynamic effect you cannot avoid. Okay? So I think the squeezing out argument is completely true. Water is being squeezed out, but it's being replenished by ice. That's what makes ice fantastic. Because the solid that you want to lubricate, it's self-lubricating. Okay? It's self-lubricating.
If you go below minus 22 degrees, then the slope of this line flips. So below 22 you can never melt ice again at pressure. And it still works. You can still skate below minus 22. So I think this argument doesn't hold there.
So, that's an interesting point. Okay? So this is just a little bit of the phase diagram. If you go to huge pressures, you get another triple point. Is this what you mean?
Yeah.
Here you have ice 1H. Here you have ice 2. This is a triple point. An ordinary ice does no longer exist in thermodynamic equilibrium. And we've seen that. At this triple point, you no longer have liquid-vapor equilibrium in thermodynamic equilibrium or in an absolute stable state. But we've seen this line was really relevant to explain lots of things. What happens here? Okay, so it still exists because ice 1 water phase transition is first order. It continues existing. Okay, of course, ice 2 is going to compete against ice 1 and will be transformed eventually, but likely not, or perhaps not, in the scales of the transformation. Okay, so
surely there's a time scale argument for squeezing out. It takes time to squeeze this stuff out. Your dynamical simulations are at a fantastic speed.
Let's talk about the speed, but that's a very important argument. So squeezing out has a scale, and the squeezing argument kills everything if squeezing is faster than the rate at which you melt. Okay, so the issue is, what is the rate of melting? What is the melt of squeezing out? And one would need to consider this to get answers. Okay.
I can see on your x-axis hundreds of atmosphere. Is this really relevant for sliders? Aren't we always on the very left of this diagram?
That's the point. Here, this is the melting point for this temperature. I think my temperature is -7 Kelvin. The melting point is 800. And this point is, I don't know, it's more than 800. This point is likely close to 1 gigapascal. So are the pressures attained at that point? I don't know. So, but anyway, it's a general argument. So the film thickness is increasing always. Whether you never attain this pressure is another matter. Yes?
I have a question. So if you put a big ice in -8 room and you put super heavy coin on it, does it tunnel through?
I didn't hear well, sorry.
Put a big ice in a -8 cold room and you put a super heavy coin on top. Super heavy.
Yes.
So it will just go through because it melts.
Yeah, I think it should go through. I think it should go through. The problem is with a coin, it will go very slowly. But with a wire, it has been done. And you can ask Daniel to do that experiment in his cold room. Or perhaps you can do it. Just for fun and have the movie done. Huh? You can do it, yes.
One thing I don't understand is that so you have the bulk ice pretty layer and then something on top and you start pushing to squeeze the water out. If you get close enough, you will get the disjoining pressure because of the...
You should, sorry?
Get the disjoining pressure that should definitely stop the two surface from getting too close. So how does this compare to too much layers?
I don't know. So you mean that the disjoining pressure is going to oppose the... Yeah. So you need to do the hydrodynamic calculation to get that done. Because the squeeze flow is the result of doing solving the hydrodynamic equation for incompressible fluids under a pressure. And so you'd need to do the calculation with an additional disjoining pressure. So I cannot respond to that question. Okay? So I think the squeezing out should not be a big issue, at least at sufficiently slow rates of pressurizing. What exactly are the scales one would need to work out? Okay, now here I am showing the same density profiles I showed you before. Those were at 1 atmosphere. Now I'm showing them at 600 atmospheres. That's a fairly large pressure. Look what has happened. If you remember the previous pre-melting films, they are indeed thicker. Now the quasi-bulk region, it's typically 2 or 3 layers thick. And here it's almost attaining the liquid density. Okay, so indeed, pre-melting films grow. Equilibrium pre-melting films grow when you impose large pressure. You can get the flow profiles, and now they look even more Couette flow-like. And if I do my simple check of how well do these films lubricate, I get very good description of the flow profile from plain Couette flow arguments, assuming bulk viscosity. I assume that the viscosity of this quasi-bulk region is the viscosity of water at that temperature and pressure. And it works very well. Okay, so I think these layers are behaving as lubricating layers.
What is in the case of the 91 degrees contact angle? The speed seems to...
That's right. Those are the slip boundary conditions. So in hydrodynamic, macroscopic hydrodynamic Couette flow, you assume stick boundary conditions, which means that the liquid is moving at the same speed as the plate. Here, the water molecules are slipping. They don't clinch to the plate, and so they don't attain the same velocity as the plate, which correspond to 1.
About the peak that goes to 3, but I think it's just a numerical artifact.
Which thing?
The time between yellow curve.
The yellow curve suddenly...
Yes, this is because of the...
No, the 1 below, close to 0 on the left.
Yes.
I think it's a numerical artifact.
There you have singularities because there are no longer almost any water molecules, and it's very...
So, as you said, there is a slip line. There is a slip. So usually, if you take, let's say, a Navier type of slip theory, there is a slip length.
Yeah.
That should depend on the angle. So
That will depend on the nature of the substrate. Okay. Yeah.
You could deduce it from that.
That's right. So here are my slip lengths.
You're prepared this.
Yeah, you
These are my slip lengths as a function of the contact angle, that is as a function of the wall. And this is the shear stress should obey this equation. There's a slip length. It's not just the thickness of the pre-melting thing, but slip length is also involved, which is the larger, the more hydrophobic you are. These results are two independent ways of calculating the slip length, that much, for the for the 1 atmosphere case, and for the 600 atmosphere case. So it seems that the slip length decreases as you increase the pressure, which looks sensible.
Negative as not really.
Okay, so these slip lengths are important. They are 6 nanometers, and the pre-melting films are typically 1 nanometer. So it's an important slip length as long as the pre-melting film remains equilibrium. If for frictional heating or whatever, it would increase a lot and become a micrometer layer, as some people claim it has, then this slip length would be irrelevant. Okay, good. Now let's study the temperature effect, but because now I am going into trouble. This is the kind of things that good referees do. I was very happy with my results at 266, and the referee bothered me with come on, do some simulations at low temperature. Okay, and here is the prediction I got at 266. Now, if I decrease the temperature, my Couette flow model is completely breaking down. Okay, this is the true simulated flow profile. This is what my model is predicting when I use the viscosity of bulk water at that temperature. Okay, recall how I was getting the length of the Couette flow, the scale of the Couette flow. It was from using this equation. So this velocity is the slip flow that I measure exactly from my simulations. The shear stress I measure exactly from my simulations. So the only thing that I am putting a bit by hand is the viscosity. I am assuming that the viscosity is that of bulk undercooled water. And it seems that is completely failing at low temperature. Okay? Now, is there any expert on rheometry here, perhaps? No? I looked on the internet. Where is the answer? Experimentally, the highest shear rates you can achieve are about 10 to the 5 seconds to the minus 1. Now, water, you do know that, is the paradigmatic example of Newtonian fluid. Is that right? Okay. What is the shear rate for Couette flow? It's the velocity of the plate divided by the thickness of the Couette flow, okay, if you like, by dc. I didn't tell you, but my experiments are done at a big sliding rate, at 1 meter second, like if you were learning how to skate, 1 meter per second. Okay, so you get 1 meter per second of sliding speed. And what is the pre-melting film thickness? So I have a huge shear rate that cannot be achieved in any laboratory in the world. Okay? And is water still a Newtonian fluid at this shear rate? That's the question.
It can be achieved, you just can't measure.
Well, like, okay, that's a good point.
Because any skater,
Every skater does it.
That's right, that's right. Okay, so what am I getting wrong? I'm saying that the Couette flow is too large. And that's because my viscosity that I have assumed is too large. If I want to recover the true Couette flow that I find, I need a viscosity that should be much smaller. So what is going on?
Shear thinning.
Shear thinning. So it's not about viscosities 1 order, 10 or 2, 3 orders of magnitude larger. It's about viscosities that are much smaller. Okay, so now here I'm plotting my effective viscosity. I can get the effective viscosity right away from this equation. From this equation. I know my shear stress, I know my rate of sliding and my slip velocity. I can geometrically look at what this is, and from that I get an effective viscosity. Okay? So I plot my viscosities during my sliding experiments relative to the bulk viscosity at the zero shear rate. Okay? And I plot it as a function of the bulk viscosity and shear rate. And all my results, independent of pressure, substrate, rate of sliding, fall on the same curve. Okay? And the simplest model for shear thinning is the Eyring model of shear thinning, which is shown here. I like this model, it's very primitive, but I like it because it only has one single parameter. So I don't need to do a large fitting effort. This is what I get. So at the shear rates that are typical initial stage of frictioning, at least, when the pre-melting film thickness is in equilibrium, you know, I'm getting a huge shear thinning effect. Okay? Very large. Okay, let's see what happens at very low temperature with some more movies. I guess I'm okay on time. How am I?
Almost done.
Almost done? Oh, okay, never mind. Let's see a movie. Okay, at low temperature, the pre-melting thing is very thin, but here is the case that Bond reported, in my opinion. You know, there's huge slip at this temperature. The wall is just passing by. You cannot see it at this stage of the film. You need to look at the initial point of the film. There's a strong slip. So likely, the molecules are acting as bearings for the substrate, and it just slips. But look at this situation. If the wall is hydrophilic, the conditions initially are thick, the friction is huge, and then you get heat dissipated. You get heat dissipated, and the pre-melting thing has increased. In the scale of a simulation, which is 5 nanoseconds. In 5 nanoseconds, I've gone from 2 monolayers of pre-melted film to 4. So wait a few microseconds and see what happens. Okay? So whether you change pressure, you increase pressure, or you get frictional heating, in both cases, you approach the melting point and the pre-melting film thickness becomes larger. Okay? So I'm going to skip these few things. And to summarize, I think that when you get controversies between smart people, this should be positive. They're not idiots. They all have reason. So Faraday was right in assuming that there is a spontaneous pre-melting film. This does self-lubrication. Okay? Now, Thomson argued that with pressure, you are likely to increase the pre-melting film. He argued bulk pressure melting. It's not truly bulk pressure melting. You don't need to achieve melting of the bulk ice. The pre-melting film thickness will increase with pressure. It's a surface effect, but it's a pressure-driven surface effect that has to do with the bulk phase diagram. So also there is self-healing against squeezing out, because you increase the pressure, you increase the pre-melting film thickness. And in many conditions where the friction is sufficiently large, then you will get heat dissipation at temperatures below the melting temperature. So this is not bulk melting. And in that sense, he was wrong. It's not back melting. You get an increase of the melting film thickness, and that's a surface effect. Of course, it's driven by the pressure difference between the metastable liquid and the melting line. And in that sense, it's a bulk effect. Okay? So they were all right. Some keys to modeling. Account for a slip length. And take into account, very important, at large sliding speeds. For a skater, it's very likely that water is undergoing shear thinning. Okay? What about the indentation? Indentation is completely important. This property is the indentation hardness, is a pressure. It sets what is the real area of contact in your problem. So you need to account for the indentation hardness. Okay? But the problem was, it is an empirical property. So what we need is working out a theory for indentation hardness. And my view of this theory is that you just need to account for the force you're exerting, creates a pressure on ice, which will melt it, and then you can only advance at the rate at which the water is evacuated. So it's this balance. And perhaps in this school there are people who can address that problem. Okay? So thanks again to my co-authors, particularly Lucas Baran, who did all the simulations as a PhD student. First of his simulations in out of equilibrium, very good work. Pablo Llombart, Boito Rigisco, and thank you again for your attention.